Swayam Prabha. Digital India. Educated India.
In this lecture, let us discuss about the strain gauge based balances further, and then we will discuss about electronic pressure sensors. So, we already learned quite a bit about the strain gauge based balances, in the sense that we looked at summing circuits, differencing circuits, and we also looked at how measurement of moment is better done with summing circuit and measurement of force is better done with a differencing circuit. So, keeping all that in mind, we continue discussing on strain gauge based balances. This is what I already discussed, and we move on to the third point straight away, that in multi component balances, the cantilever or sting needs to be specially machined for suitable positioning of the strain gauges for measurement of a particular component. For example, if we take a 3 component balance which can measure normal force, axial force and pitching moment, the experiment is usually performed by setting the model at different angles of attack and recording the forces and the pitching moment. So, you will be getting those in the body axis system. The normal and axial forces which would then be recorded have to be converted to lift and drag forces, and for that what you need to know is the angle of attack. So, once you apply the angle of attack, you can easily obtain the lift and drag forces from your normal and axial forces that you have measured. We will of course look at a schematic diagram of a 3 component balance in the next slide. If you are interested to go for still higher number of components in a balance, let us say you are interested further to measure side force and yawing moment, for example, then the very same principle gets extended. So, whatever principle you are using for measuring lift and pitching moment gets extended for side force and yawing moment measurement. Only thing is that the strain gauges are to be bonded on the side surfaces of the sting instead of top and bottom surfaces of the sting. For example, if we try to draw a very simple representation this way, that this is your sting which is more like a cantilever beam, though we are not showing the support here, which will be here somewhere. Now, we were talking about placing load cells on top and the bottom surfaces for obtaining the lift and pitching moment, for example. However, if you are interested in obtaining the side force and the yawing moment, you would be utilizing this side force and the one which is opposite to it, but is visible, but is not visible in this view, because that is the direction in which the sting balance will get deformed under the action of a side force and yawing moment. So, we are basically changing the plane in which the deformation occurs or the strain occurs, and therefore, the mounting of the strain gauges have to be on the side surfaces instead of the top and bottom surfaces. So, this is the sketch we were talking about. This is a schematic diagram of a 3 component balance for measuring normal force, axial force and pitching moment. It is a very rough sketch though. This is the sting balance support, and these are all metallic sections of course, and what you can see is that strain gauges are mounted at different locations, which of course is done after suitable machining. and then these are basically hollow sections. The sting balance is made hollow, so that the deformation in the sections are of slightly higher order, so that you can record the strains even with the slightest change in the loadings. You need to look at the locations of the different strain gauge 1, 2, 3, 4 for example. What do they form? They are available here in a differencing circuit mode for obtaining lift. Differencing circuit, of course, you can make out with C and T opposite to each other, and you also notice that they are kept quite far apart from each other. This was the Z2 minus Z1 maximization that we were talking about some time back. Again, let us look at 9, 10, 11, 12, which are supposed to be measuring drag. 1, 2, 3, 4 was for lift, and then they are kept on a different section closer to the model, and there the section can be kept a little slender, so that the drag force can be accurately measured. Remember that in an aerodynamic configuration, the L by D ratios are expected to be high, and therefore, the drag forces are pretty much lower than the lift forces, but they have to be recorded or measured with accuracy, and therefore, that much smaller force also needs to be recorded properly, for which the sectional thicknesses have to be accordingly designed. And then again you apply the differencing circuit, in that case 2. So, you have tension, compression on opposite sides, and not only that, you also try to maximize the distance between them as far as possible. Going to pitching moment, you have resistances 5, 6, 7, 8, which you can see are much closer to each other compared to the differencing circuits. So, this is where you see the difference. They are kept much closer as far as you can approximate them, and then they are put in a summing circuit, in the sense that compression opposite to compression, tension opposite to tension, that gives you the summing circuit. And therefore, you have to design appropriate sections, you have to mount the strain gauges appropriately with appropriate distances between each other, and then connect them appropriately in Wheatstone bridge configurations, so that you are able to get either forces or moments out of them. So, this 3 component balance configuration gives us some idea in that regard. Let us look a little further. Let us say if you are interested in measurement of rolling moment. Earlier we were talking about measurement of side force and yawing moment, and we found that it was somewhat similar to measurement of lift and pitching moment. Only thing is, mounting of the strain gauges have to be on side surfaces instead of top and bottom surfaces of the strain gauge. But what about rolling moment? Here the section is usually differently designed. So, let us imagine that the main sting body is circular. If it is that way, then it is machined in a form like this in one part of it, where the strain gauges related to the rolling moment measurement are to be bonded onto the sting balance surface. So, we find that some kind of a section like this is machined, and on the 4 surfaces 4 strain gauges are mounted. Remember that when there is a rolling moment, it will tend to move like this or like this, and then a section of this kind will be much better sensitive in trying to record the rolling moment. Therefore, the sections have to be appropriately designed to make them sensitive for measurement of a particular force or a particular moment. This gives us a good example of that. Beyond all this, there is also the problem of cross coupling between the different load components or interactions. So, what is meant by that? Let us try to discuss that. So, it is desirable to design a strain gauge balance to make each bridge sensitive to only one load component. Let us say the bridge which is measuring the normal force only measures normal force, it does not respond to any other force application. However, it is not practically possible to eliminate completely the interactions due to other load components. This is a fact of life, and these interactions can be both linear as well as non-linear. Interactions, modeling them as linear is somewhat easier, modeling them as non-linear interactions is further more complicated. But again, real world most often shows up non-linear behavior to quite an extent. Therefore, the different loadings tend to get coupled when it comes to the measurements. This we have discussed to some extent when we were also talking about mechanical balance, if you recall from an earlier lecture. Well, then in the present context of electronic balance, if you have a 6 component balance, each bridge output is a function of all 6 components, 3 forces and 3 moments. And let us say for simplicity we consider only linear interactions. If we do so, then we can write any one load component in the following form. We have shown a formula here for indicating the way we should represent it. This is the formula. What do those terms mean? First of all, Ri is basically a reading of the ith component. That ith component may be lift, drag, side force, pitching moment, rolling moment or yawing moment, any one of them. So, the different forces are written, the different moments are written, and they are accompanied by coefficients. The coefficient has an index, I is coming from this index and the other part of the index is corresponding to the particular force of the moment that we are referring to and associating it with. Note the nomenclature here. If you vary I from 1 to 6, so that all the 6 components are covered, then you will actually have 6 such equations for each of the 6 readings, where what are those K's? Those K's are nothing but calibration constants. So, 6 equations each containing 6 calibration constants makes it 36 first order or linear calibration constants, and we do not know them initially. Therefore, they have to be obtained experimentally. This is what makes life very difficult for an experimentalist, but this has to be done very systematically, without which the balance is not usable. So, all the 36 coefficients can be calculated by loading the balance with each component independently, and then the repeating of the procedure 36 times to get the 36 coefficients. There is no easy way out. You have to do it and you have to fill up this information before the balance becomes usable. Once you are done with it, then you know the values of all these coefficients, and therefore, they would be basically plugged in order to interpret your meter reading or display reading in terms of the load that you are measuring. So, with that we end our discussion on balances. Now, we move on to a discussion on pressure measurement using electronic systems. So, we are looking at a model where you can see that there are pressure ports located on the surface of the model. So, we will try to highlight once again. So, these are small pressure ports, as you can see. This is basically an aircraft model which is sting mounted. The sting is here at the base, and you can see that it has broadly a delta wing configuration and pressure ports located on different portions of the delta wing and other parts of the aircraft, and therefore, we are interested to measure the pressure distribution on this body which is mounted within the test section of a wind tunnel. Let us briefly introduce electronic pressure gauges, the main points. So, when we talk about electronic pressure gauges, we are basically talking about pressure transducers, and they can measure a wide range of pressures and with very good response in general. We discussed about how they are superior to their mechanical counterparts in terms of response time, in terms of measuring very high or very low values, in terms of their ability to capture transients, ability to capture unsteady pressure with very high frequency, etc. So, these are advantages which you cannot achieve using a mechanical pressure sensing system based on pitot tubes or pressure ports coupled with manometers, and therefore, electronic pressure gauges. When you talk about very low or very high pressures, that means you are able to cover a wide range of pressures depending on your need, and accordingly the pressure transducer is designed for the range that it is supposed to be operational for. The range that we have available is broadly 10 raised to power minus 4 to 10 raised to the power of 5 psi. Now, psi basically stands for pounds per square inch, and if you do the unit conversions, you will find that 1 atm is approximately equal to 14.3 psi. So, you are encouraged to do the conversion yourself at home and check for yourselves. So, you are now familiar with different units of measuring pressure: bar, atm, Pascal, which is the same as Newton per meter square, pounds per square inch, etc. The electrical output signal from the transducer is produced by deflection of an elastic sensing element due to application of fluid pressure and consequent sensing of that deflection by an electrical sensing element or elements. That means, pressure causes a deflection in an elastic sensing element, and then that is converted into an electrical signal or current using electrical sensing elements. Well, the strategy remains exactly the same as what we have discussed in the case of electronic balances as well, but the configuration is different. So, let us see configurationally what is the difference between what we have seen in a balance, where we had used a cantilever beam like setup which we call as the sting balance, and what we are calling as a pressure transducer. So, in the pressure transducers, most often the elastic sensing element is a diaphragm. We are no longer talking about a sting or a cantilever beam, but a very thin diaphragm which can respond to pressure changes. It is usually a thin circular plate fastened around its periphery to a support shell. Usually stainless steel or beryllium copper is used for the diaphragm material. So, what are we looking at? In side view, it will look somewhat like this. So, you have a shell like we said. So, in top view, it is like this, right, and on top you have a very thin diaphragm. So, let us say you have two different pressures from bottom and top. So, there is a differential pressure based on which this diaphragm will deform, and of course, you will have to have the electrical sensing elements, which means the strain gauges. So, if you bond them on or connect them on that diaphragm appropriately, so that a pair of them are in tension and another pair in compression, then obviously the strategy would be again to build a Wheatstone bridge out of those resistances, configure them in a differencing circuit sense, and make them respond to the force, which is basically coming out of this differential pressure into the area on which it is being applied. So, let us say if in this configuration the pressure causes tension here and a compression here, then that automatically will help you configure a Wheatstone bridge. The electrical sensing elements are metallic or semiconductor strain gauges as usual, which are bonded to the surface of the elastic sensing element. Variable resistance pressure transducer use strain gauges. We already discussed, which comprise of differencing Wheatstone bridge circuit configurations. Their resonant frequency is of the order of 1 kilohertz. There is another category called as piezoelectric transducer, where voltage is generated when pressure is applied due to the squeezing of the piezo crystal. That means, the applied pressure is squeezing a crystal, the piezo crystal, and that helps in generation of a voltage. Therefore, these kind of transducers are self generating. That means, you do not need an excitation voltage for them to respond and give you an output voltage. They can generate their own voltage based on the applied pressure. Therefore, the output electrical signal comes on its own. They are very high in terms of resonant frequency, which can go up to 500 kilohertz or even more in the megahertz level. The time response of a pressure transducer is not vital for obtaining time average pressure. However, for measurement during short transients or measurement of unsteady pressure, superior time response is absolutely critical. Also, when you are looking for high time response or superior time response, the transducer must be flush mounted or be connected by very short tube lengths. That means, the point at which you are recording pressure, the transducer needs to be absolutely flush mounted to that point or very close to that point, but certainly not at a far off point connected using a pressure tubing. That is a very faulty way of measuring time dependent pressure. Let us look at a very interesting configuration which has remained in service for long in this electronic pressure measurement world, which is basically the concept of pressure scanner. So, these days piezoresistive transducers have become much cheaper, much affordable, but there was a time when they were extremely expensive. So, at that time the strategy was to use a single pressure transducer to measure pressure from many ports of a model mounted in the wind tunnel. So, this was possible through a pressure scanning or pressure scanner system. So, this was primarily a constraint due to the expense. During this period, pneumatic scanning valves called as scanny valve were produced, and they were very popular for a long period of about 40-50 years. In a scanny valve setup, a single transducer of excellent quality was connected or interfaced with each of the model pressure ports sequentially. That means, one port at a time interfaced or connected with a single transducer, which is of a very high quality. So, if we look at the sketch here, that is what it is talking about. So, you have one high quality transducer which is connected to your data logger or PC, data acquisition systems, etc. And pressure is coming from different points of the model into this pressure scanner, which engages one pressure with the pressure transducer at a time. That means, one port is interfaced with the pressure transducer at a time, and therefore, it records the pressure from that particular port for a short duration of time, transfers it to the data logger or to the PC, and then indexes or reorients the system so that another pressure port comes into an interfacing with the pressure transducer freshly. So, that system is basically built in this pressure scanner. The position transmitter or encoder electrically indicates the port that is being measured currently, because from time to time there would be a rotation and thereby one particular pressure port only at a time will be interfaced with the pressure transducer. Remember again that since we have only one pressure transducer in this setup, this indexing will be required. This interfacing with different pressure ports one at a time sequentially would be required. Let us say you have 100 ports on the model, then in a given time you would move from port 1 to port 2 to port 3, complete up to 100 and then again come back to port 1, and over short duration delta t you try to record the pressure coming from each port through that pressure transducer. So, the transducer is sequentially connected to the various PX ports by a single hole in the rotor which terminates at the collector hole. So, there are design related details which are being mentioned over here, but the basic idea we already talked about. As the rotor rotates, this collector passes under the PX input pressure ports in the stator. Because of the extremely small travelling volume, the scanning rates of 20 ports per second are possible. The stator is elastically connected to the block in a manner which allows the stator to follow the surface of the rotor. Thus, the pneumatic forces at each port which tend to blow the rotor away from the stator are withstood by the thrust ball bearing. Each PX pressure is elastically ducted from the block to its port in the stator. So, these are more details about the actual configuration which you can see even from this picture, and you will understand better if you go through this part. But the most important part is to understand that we do have only a single transducer in this setup, and we have to measure pressure from many points of the model, and the pressure scanner enables us to do that. In later times, piezoresistive transducers became much more affordable, and then what happened was that large number of pressure transducers were packed within compact pressure transducer setups, and now you can have one transducer measuring from one port only at a time. This is another schematic diagram of the electronic pressure scanning system we were talking about. So, this is the Scanevolve configuration. You can see that 8 number of ports are actually there in the model, which is shown here, and at this point the port 2 is being read by the pressure transducer. It is interfaced with a signal conditioner and further with the digital display or PC, and the pressure tubes connect the Scanevolve port with a model pressure port. So, these ports and the pressure tubings, so these are the tubings are schematically shown, and this Scanevolve can be indexed manually. That means, you can rotate it from one port to the other manually or by using a solenoid control system. Moving on to little more modern systems, where as I said that you can actually have them in much more compact setups, and these compact setups can contain 64 transducers within a small volume like this, more like a rectangular biscuit. The highest length is of the order of 10-11 centimeters, and then 4 centimeters and 1.5 centimeters along the other two directions. And that is because piezoresistive transducers have become much cheaper these days. They have very high natural frequency, the data acquisition rates are much higher, they have very small dimensions, and therefore, they can be packed into and accommodated within wind tunnel models. That means, you can have a fully instrumented model with the pressure transducer sitting inside the model itself. So, it has become that compact, and as you understood that when you are trying to make unsteady pressure measurements, the transducers need to be extremely close to the measurement point. So, having an instrumented model with these pressure transducers located within the model is very advantageous. The reference pressure is sent simultaneously to all transducers. So, there is a reference pressure port which may be either open to atmosphere or it can be fed with some constant pressure source, or it may be connected with the wall pressure port of the wind tunnel. So, there needs to be a reference pressure which can be simultaneously provided to all the transducers that you have in the setup. A large number of metallic tubings are coming out of the setup. So, that you can figure out that there are pressure transducers inside which are interfaced with those, and therefore, a large number of pressure transducers are actually located here within. Very often in these systems, a control pressure additionally is required, which may be in the order of few tens of PSIs or few ATMs basically, and it has to be applied with some control pressure, it has to be applied to a control pressure port, so that you can function the pressure transducer setup in different modes. It can be a measurement mode where you are recording data from a model, or you are freshly calibrating the transducers, or you are purging and cleaning the transducers to remove clogging. So, there are different features which have been now included. They have been made compact, they have very good frequency response. So, a lot of advantages have now come into these systems. A typical setup may look like this, where you have a couple of these transducers positioned here inside a much larger perspex box, and the associated setups are there which can provide it the power supply, and you see the pressure tubings going out of the transducer biscuits, and they would be connected with the models. So, in this lecture we discussed about strain gauge balances in the beginning. The placement of strain gauges on the balance and coupling or interaction effects were discussed. Subsequently, electronic pressure gauges were discussed. The concept of a pressure scanner to interface a single pressure transducer with multiple model pressure ports was discussed, that is basically the Scannival model. Further, more modern units with multiple pressure transducers, each connected to a specific model pressure port and housed within a single system, was also discussed. Thank you.